Okay, so we might get underway, everybody. So welcome, everyone, to today's AIRAH webinar. My name is Marika Rekla, and I am AIRAH's Engagement and Program Coordinator. Today's Streamline is brought to you by AIRAH, and this webinar will review the case study in equilibrium, and it will also go through an example of a pump system, DTS solution. So just before we get underway today, if you have any questions throughout the webinar, please use the Q&A function that's located just at the bottom of your screen, and we will allocate some time at the end of the presentation to go through any questions you may have. So now I'd like to introduce to you our presenter for today, Grace, who will be taking us through today's session. So Grace, I might pass things over to you now to get us underway.
Excellent. Well, just to give a quick introduction to myself. So I'm Grace and I'm a principal consultant at Delta Q, which is a energy efficiency consultancy. My involvement in Section J was I was part of the team that was responsible for making revisions to the 2019 NCC from 2016. So my colleague, who was the main developer of the pump system, is not here today, but I guess that gives someone like myself a bit of a context around why things were set up the way they were. So just to go through an agenda of what we'll go through today, there's really only two big parts to my webinar or presentation. In the first part, we are going to go through an overview of the new Section J requirements. It is quite a change from the 2016 requirements. Some of you may already be familiar with it, given that we have a 12-month transition period, and some of you may just be starting to use the new requirements to design your systems. And then in the second part of this presentation, I'm going to go through a work example using the pump system calculator, which has been developed by the ABCB. You can go through manual calculations yourself if you like, but the pump system calculator really makes things a little bit easier for you to show compliance for DTS. Okay, so the pump system's requirements are covered under the deemed to satisfy or DTS requirements in Section J, Part J 5.7. I will note that there are also pipework installation requirements covered under Part J 5.8, which we're not going to discuss today, and it's also not going to be the focus of the case study that will be published in Equilibrium for August, September. But it's still important for you to make sure you comply with those requirements when you are designing your system. These pump system requirements only apply to air conditioning systems. So if you're talking about, things like hydraulics, domestic hot water, these requirements won't apply. So let's have a look at the new requirements. It's basically summarized into two ways to comply. The first method of compliance that you can use is the component-based compliance. You'll be looking at two parts of it. First is looking at the pump efficiency itself, and then you need to comply with straight ductwork requirements. We will go through those details in the next few slides, but you just need to remember that there's only two parts to that components-based compliance. The second way that you can comply is to use a system-based compliance. So that's where you're not looking at the individual components. So for example, if your pump failed in itself, you may still be able to comply if you look at it from a system perspective. The system-based compliance is based on looking at the pump watts per liters per second, and it's doing a comparison of your proposed design versus a reference system. As a reminder, this this is quite different from the previous requirements that were purely based off a watts per square meters allowance for your pump power, which was then also matched to your cooling or heating load. So let's go through the first method now, which is your component-based compliance. So as I mentioned before, when you're looking at your components-based compliance, there's two parts to it. So you have your pipework requirements, which only applies to straight pipework. It does not include any of your fittings in terms of pressure, maximum pressure drops or pressure losses. And it also doesn't apply to straight pipe work where your velocity is less than 0.7 meters per second at design flow. The second part of the components compliance refers to your pumps. So that's looking at your pump efficiency. So for your pumps, there's two types of pumps for which you may need to comply with. The first type of pump is a circulator pump with a hydraulic power output of less than 2.5 kilowatts. You can see that in that image, that's the one in the middle. And it would typically be seen in your primary loop of your heating hot water system, perhaps, or as I said, your domestic hot water system is not included in these requirements, but those are the sort of pumps that you will see as well. Now, if you had a circulator pump that was less than 2.5 kilowatts hydraulic power output, then the compliance requirement for you is something called the Energy Efficiency Index, or EEI, being less than 0.27. The EEI is a calculation based on the European Union Commission Regulation number 622/2012 edition. It's all in the code itself, and if you wanted to have a look at how it's calculated, you can also download it for free by just doing a web search. But basically, an EEI is a metric that defines how efficient your pump is relative to a predefined reference. So there's a reference pump in the EU document, and therefore, if you had an EEI of 0.28, it means you're less efficient than your reference pump, so it wouldn't comply. The other type of pump that you need to comply with is any pump that is not a circulator pump. Now, if you're not a circulator pump, then your compliance requirement is a minimum efficiency index, or MEI, which is also taken from the European directives. But it's a different document. It's the EU Commission Regulation number 547/2012 edition. The requirement is to have a MEI greater or equal to 0.4. And what it effectively means is that if you have an MEI of 0.4, there are 40% of pumps which perform worse than you. Okay, so with the straight pipe work requirements, the maximum pressure drop per meter pipe work is defined and is different depending on whether your system is a distributive or non-distributive system. Depends on how long your pump system will operate. It depends on what your nominal pipe size is, or nominal pipe diameter is, and whether your system is a constant speed or variable speed system. So let's look at the first element now, which is your pump efficiency. Remember, this is our EEI and MEI. This data can typically be obtained from your pump manufacturer technical data. So for example, if you went on a ground force pipe pump selection interface. You can put in your head and your flow that you need, and it'll tell you what the MEI or EEI is. So it's quite straightforward. For EEI requirements or your circulators, you also need to determine what your hydraulic power output is. Now, this can be calculated based on the formula Q times H, or your flow rate times your head, and then you multiply it by some constant, including your fluid density or gravity. And you would need that hydraulic power output for input into the pump calculator. Now, if you don't want to calculate it, you can also just get it from your pump supplier. With the MEI, it's basically a formula that looks at your pump best efficiency point, or BEP, your flow and your head at multiple points. So it's looking at, it's almost like if you knew a chiller system, it's almost like an integrated part load performance, where you're looking at performance at 75% of your best efficiency point, looking at performance at 100% of your best efficiency point, and then you're looking when it's overload, which is 110%. You don't really need to worry about the formula. Again, as I said, this is generally information available from your pump manufacturer. What I've shown here on the bottom left corner of the slide is just to show you on the pump curve where the BEP generally is. So you can see here that you want to be selecting the points where it's about 74% efficiency. The other thing to be careful about is the BEP from a pump supplier is generally calculated based on the maximum impeller diameter that is available. If you're buying a pump and you are trimming the impeller yourself, your BEP may be different from what is specified on the technical data or technical documentation. So you just need to be careful of that, because you need to be using the maximum impeller size. If you were getting it pre-machined by the pump manufacturer and they already give you a BEP corresponding to the impeller diameter that you're installing on site, then it'll be fine. You can just use the technical data provided by the supplier. Obviously, where you are using a variable speed application, you would still be using the BEP corresponding to 100% speed and at the top line of the pump curve. On the bottom right here, I've just shown you a snapshot of the formula taken from the European standard. As you can see there, it's based off a number of constants, which looks at your flow rate, and it looks at your pump type as well. And there'll be, if you go into the document itself, you see lots of tables that tell you what the specific constants to apply to this formula is. The next element that you need to comply with is straight pipe work. You're only really looking at the index run of your system. It's based on the average pressure drop pascals per meter. So if you had, as you're aware, in a pipework system, you end up with lots of different stretches of straight pipework. What you would do is you would take the sum of your total pressure loss or pressure drops across the straight pipework component only, and then you divide it by the total length. So what that means is that if you have one element of a straight pipework that doesn't comply, it doesn't really matter because it's going to be averaged out. I've already mentioned this, that your straight pipework requirements are not affected by, well, clearly valves and fitting. Pressure drops are not considered in the code, even though you need to do that pressure drop calculation related to valves and fittings to determine what size you need your pump at. And as I mentioned, the smallest compliant pipe size, where it results in a pipe velocity of less than 0.7 meters per second at design flow, wouldn't need to comply to these requirements. The straight pipe work requirements would vary based on variable or constant speed, whether you have a distributive or non-distributive system. So in most systems, it wouldn't be a constant flow because of the different branches to it. And if you have different branches, then generally it will be distributed flow, distributed system. And then you can see there, dependent on your pipe diameter as well as your annual hours of operation. Now, if you had a pump that was 2 or 3 speed, so you've got 3 speeds function, but they don't dynamically vary their speed based on demand, then you will consider them as a constant speed pump. So just to show you the tables that are in the code, on the left there, we have a table showing your maximum pipe work pressure drop for non-distributive variable speed systems. And then on the right side, you have the maximum pipe work pressure drop, also for non-distributed systems, but it's constant speed. So in blue there, you can see that if you were running a constant speed system, your maximum allowance or pressure drop allowance is lower compared to a variable speed system. In orange there, you can see that as you increase your nominal pipe diameter, so as your pipe size increases, the maximum allowable pressure drop in the code also reduces. So if you had a very small pipe size of say maybe 20 mils, your requirement is 400 pascals per meter, you can't exceed it. If you had a larger pipe, then you're only allowed 300 pascals per meter pressure drop, average pressure drop. In orange there, that's showing you the impact of increasing your annual hours of operation. So as you increase the number of hours that your SIP pump and pipework system will operate, then the pressure drop allowances reduces. In blue here, what I wanted to show you was just for a non-distributive system versus a distributed system on the right. And you can see that for the same pipe size, both operating variable speed and both operating more than 5,000 hours per annum, the requirements for a distributive system is more stringent compared to a non-distributive system. So the second method that you could use to comply is the system-based compliance method. So I like to use a food analogy for this because it's easy to visualize. So if you were using a component-based method, which is your method 1, you may individually decide that for breakfast, you're going to pick healthy elements to include in your breakfast. So you might pick an avocado, some pine nuts, eggs, and some bread, wholemeal bread. And you might be calculating the health benefits of each element in itself. However, if you were to apply a system-based approach, which is the second method, you can see here that what you'll be doing is on the left side of the image of your breakfast showing your eggs, avocado, and toast. You would be possibly just analyzing what the calories in that whole plate would be, rather than trying to look individually at the eggs, avocado, and bread type in itself. Now, in a system-based approach, we will be comparing your healthy reference breakfast, which is the DTS reference, versus a proposed breakfast. So you might say, hey, what if I had a different type of breakfast with some strawberries, olives, and I still have eggs in there, but I'm going to have some prosciuttos in there. How healthy is it compared to my reference breakfast? And that's exactly what you're doing in our pump system or pipework system here. What you'll be assessing is the calories of food is the watts per liters per second associated with your pump hydraulic power. Again, comparing your DTS reference to your proposed design. The reason why the system-based approach was introduced was to provide some flexibility for innovation and for designers to, I guess, match custom applications to your building. So let's have a look at the case study or the work example now. So just some background information of the pseudo-fictional building that we're working on. So we're looking at a very tall building, 55-story building, but we're just going to focus on the mid to high-rise floors, which is levels 25 to 54. It's a tenant condenser water system. We have 3 pumps in a lead lag standby configuration in the plant room. And because there's lots of branches, you can see on the right there, it sort of tees off to multiple floors. It's a distributed system. And because it's a tenant condenser water system, it also operates 24/7. So more than 5,000 hours per year. We do have variable speed pumps in place. So this will be a variable speed system. And then we have our index run on the bottom level, on level 25, going to the index pack unit. So we'll be using the pump systems calculator. You can download it at the ABCB website. And I would recommend that before you start on your next project, always go to the website to see if there's a more recent version that has been released by the ABCB. It's a spreadsheet, Excel spreadsheet format document, which has macros in place. So what you may need to do is to make sure that you have your, I guess, trust center settings to allow macros to run, and also to allow, I guess, files that are downloaded to run. I think there are also some known bugs with the spreadsheet, which they've tabled it under the help button once you open the spreadsheet. Okay, so when you open your pump system calculator, the first thing you want to do is just to set out your pump systems information. So you have your building name, your description, project number, designer and company. None of that project information actually affects your compliance checks. You just need some data in there to let the spreadsheet run. And then you can see here that you can actually run multiple systems. So, you know, in a standard building, you probably have your heating hot water system, your chilled water system. You may have 2 sets of condenser water systems. You can actually assess compliance of those systems all in one spreadsheet. And that's why you can actually put in the different systems, and they'll assess them individually. I will note though, if you're putting a lot of data in, it may be better for you to use multiple spreadsheets rather than do them all in one to avoid the spreadsheet crashing. It's also quite computationally intensive. So even with this system, for example, it did crash a couple of times on my own system. So I think my recommendation to you would be to use multiple spreadsheets to assess compliance. Once you've done that, you want to then set up your pump system summary. And as you can see here, what you need to input is the pipe system type. There are options for you to pick whether it's a distributive system or a non-distributive system. So here in our case study, we have a distributive system. The system speed control You can select whether it's variable speed or constant speed. In theory, I don't know why this is reading constant speed. It's probably the wrong screenshot, but this would be variable speed for our case study. And then here we have operating hours per annum. There will be choices for you to put in either more than 5,000 hours per year, between 2,000 to 5,000 hours per year, or less than 2,000 hours per year. So this is all fairly straightforward. Now, once you've done all of that setup, we then go into the different methods of complying. So we're going to start looking at using the component-based pathway first, and see how we go. So before you go into inputting all your information in pump calculator and assessing compliance, there's a whole bunch of work that most of you would be experts at, which indeed I'm not going to go through pipework design in this presentation. That goes into, you know, designing the size of your pipework, how it runs through the buildings, and what sort of fittings you would use. When you're doing your pipework design, you would probably be considering, you know, what your fluid velocities are to avoid air entrainment. You'll be considering what the upfront cost might be based on your design. If you had lots of large pipes around the system, it might actually end up being really expensive in terms of upfront cost. When you are doing your assessments, you'll be considering your NPSH or net positive suction head that's required. You might be considering what the noise is in terms of how fast the velocity is flowing. You might consider the life cycle cost, so the cost across the whole life of a pump, 15 to 25, 30 years. You need to consider how you can avoid cavitation, and you may also need to consider, what the heat gain or loss is, because it affects your coil delta T. Obviously, you'll also be looking at fittings and valves friction losses, which are not considered. There's no requirement or compliance requirements in the NCC at this stage. So when you're doing all of these, you will likely be referring to the AIRAH DA16, which is a guideline for you when you're sizing and designing your pipework. So most of you will probably have some form of spreadsheet, or you might have a software similar to the image on the right, which I've just taken from the AIRAH DA16, assessing the pressure drop for your straight pipe work, and then on the right side, your fittings. Now, once you've done all of those, we're going to move into pump selection. So from the calculations that were conducted, we have assessed that the pump head pressure requirements is 200 kPa. And the flow that we need is 35 liters per second. So what we then did was just jump onto, in this case, it was the Ground Force website, and pick the pump that matches what we want. So you can see here that this is a long coupled end suction pump. We have a 2-pole pump motor, which stands at 2,940 RPM. We have the flow and head. And then you can see here on the bottom right, that's the MEI, or the minimum efficiency index. So once we've selected our pump, we then want to put it into the pump system calculator. As you can see here that we have picked other pump for pump configuration. The only choices that you have is whether it's a circulator pump, less than 2.5 kilowatts hydraulic power output, or any other pump. Then you have the pump design, where you can see there's multiple options there. To be honest, I think in a HVAC standard configuration, you're most likely looking at only the end suction oil bearing, which is your long coupled pump, or a closed coupled pump. Personally, I haven't really encountered the other two pumps, but if you had those pumps, you can put them in. And if you can't find a pump that matches any of the above options, then you have an other option that you can pick. The pump stage for this case study is a single stage pump, so we don't have multiple impellers within that same pump. Therefore, it's a single stage pump. I think it's quite rare, again, in the applications that we generally see, to have multiple series impellers within the same pump. And then finally, we have the pump speed, where you can select either it's a 2-pole, 4-pole, and I think perhaps even a 6-pole might be available here as an option. So you can see here that's 2,900 RPM typically, which agrees with what we saw before, which it runs at 2,940 RPM. Then the second step is for us to check the pump compliance. Now there's two options here in the pump calculator. One is we already know what the MEI is because we've seen it in the technical data from the pump manufacturer. So we can just use the simple method. So I can put in 0.7, which is what I've obtained from the pump data sheet just before. And can see straight away that the pump calculator says that it satisfies clause J 5.7. The issue is that if we were to go through the rest of our compliance items and we found that we can't comply using a component-based approach, we may need to use a whole of system approach. If you were to use a whole of system approach to comply, you must use the alternate method approach, which I'll go through in the next slide. So if you were to use the alternative approach, the spreadsheet automatically calculates the MEI for you using the pump best efficiency point. So you can see here that what I've done here is we take the water flow rate, which is 35 liters per second. We have the system head, which is 200 kPa. And then the BEP of the pump is taken from the pump curve, which is 82.4%. The spreadsheet automatically calculates using the EU formula what your required MEI is, or your minimum level of that you need to comply with is. So here the spreadsheet told me that my minimum MEI needs to be 78.1%, but because my pump selection is 82.4%, which is higher than the requirement, it satisfies clause J 5.7. So that's all good. Now let's look into the last component of or element of our component-based compliance approach. So it's now looking at straight pipe work. What we've done here is basically to take all the information that we've done on a separate spreadsheet to do the calculations, selected only the straight pipe work elements, and then dumped them or done a copy and paste into the pump calculator spreadsheet. So you want to make sure you don't put any of your fittings or valves information in a spreadsheet. I will note that this is quite long. It is best if you can summarize the information that you try to combine stretches of straight pipe work where you can, because the spreadsheet calculates each line and each change to each cell every time you make a change. So you can imagine that when here we had 106 lines, every single cell will be changed, either the flow rate or change the diameter or change the length. Took quite a long time for the spreadsheet to calculate, automatically calculate. So what the pump calculator will do for each line or each straight pipe work stretch is to, they will automatically calculate your velocity, and velocity check just tells you whether it would be less than 0.7 meters per second at design flow. If it's less than 0.7 meters per second at design flow, then it says not applicable, so you don't need to comply with anything. It also automatically calculates the pressure drop associated with that stretch, and the maximum PD is just what the code says your maximum pressure drop can do. And then it will tell you whether you're compliant or not for each little stretch. So you can see here that we have a few exams from the compliance requirements. You can see a few which is in green, which says that for that stretch, it meets the requirements. And then you can see a few red lines where that stretch of pipework doesn't meet the requirement. But that doesn't really matter because, as I mentioned at the start of this presentation, we're looking at the average pressure drop across the all straight pipe work. So on the bottom of the pump calculator, it will automatically do an arithmetic calculation where it just takes all your straight pipe work pressure drops, sums them, and then divides them by the total length that you've entered into the calculator. You can see here that on a component level, all the straight pipe work components satisfies the code because my average pressure drop of my system is 135.2 pascals per meter, whereas I'm allowed 290.5. There is also a simplified method available on the pump calculator where you don't have to enter all of your straight pipe work stretches. All you need to do is you can enter the average pressure drop that you have calculated yourself on a separate spreadsheet. You just need to tell the pump calculator what pipe diameters are available, and they just use a simplified method where they look at all the tables and say, okay, well, the maximum pressure drop that's allowed is 180. You have told me that your average pressure drop is 100 pascals per meter, therefore you satisfy the code requirement. Again, with the simplified method, you can't use it if you are resorting to a whole of system compliance approach later on. So what we did here in the case study was just do a few tests to see what happens to the maximum pressure drop allowed if we made some design changes. So the first test was where we reduced the operational hours to business hours only from 24/7. So we've reduced it to 3,120 hours per year. And you can see in the table that under test 1, the maximum pressure drop allowable for my system that runs less hours per year is now higher at 400 pascals per meter. We also did a test which said, well, what if my system in my case study operated as a constant speed system instead of variable speed? And you can see that when it operates as a constant speed system at the same number of hours per year, which is 24/7, my maximum pressure drop allowed is more stringent. So it's only 164.4 kPa now. So what we did here with our case study was to change the pumping control arrangement. So this is now fictional. It's probably not very practical, but the design team said, hey, what if we only had 2 pumps running duty standby? We're not going to change anything else in the pipework design because it's going to take us too much work, but we only want 2 pumps. So instead of lead, lag, standby, we're now only doing duty standby, which means that at the plant room level, instead of 35 liters per second, now I need to have a flow of 67 liters per second. And my pump head pressure is now 300 kPa, just because there's been increased pressure losses in my plant room itself associated with the fittings. Now for this new pump that we've selected, we don't know what the pump MEI is for whatever reason, but we do know that my pump best efficiency point is on 78%. And we selected a 4-pole or about 1500 RPM and suction long couple pump. So again, just going through the steps that we've gone through before, looking at pump compliance. We put in the BEP, which is 78%, updated flow rate and a system head. And now we don't comply because our BEP is 78% compared to where we need to be, which is 81.3%. Why don't we check if our straight pipe work complies before we figure out what we do next? So again, we've just updated our pump pipe work details in the spreadsheet. You don't have to worry too much about, I guess, the detail in a screenshot, but what we can see here is that even though there's more red lines now because my pump, the stretches of pipe work within my plant room at the start of my leg, there's plenty of legs where it doesn't satisfy Section J requirements, but on a average assessment level, I comply with clause J 5.7. So we're not too worried about straight pipe work. But because my pump efficiency doesn't comply on a component-based level, I need to figure out how we can meet Section J compliance requirements. So we're going to test out using the system-based compliance now, or method 2. Because we've used the more complex methods, so instead of just taking the MEI directly from the technical data and entering it in, we've used the best efficiency point to calculate it. And we've also used on the straight pipe work section, we have entered all of the detail into the spreadsheet rather than just taking our calculated average pressure drop per meter and entering into the spreadsheet. The spreadsheet is automatically calculates the whole of system compliance easily by you just clicking onto the report tab in the spreadsheet. So here you can see it's actually summarized all of the information, and it's told me on a component level satisfaction, circled in red, that my pipe work component level on a component level is satisfied Section J, but on a pump level, for the pump, it doesn't satisfy it, and therefore overall it's not satisfied. And then right on the bottom, it automatically calculates the system level compliance. And you can see here it's got a whole bunch of percentages where it says that my pump is minus 46%, so it's more efficient. My pump is plus 4.2%, therefore it's less efficient. But when you multiply them both, I end up with motor power that's minus 43.8%, and therefore overall I meet the code. This is actually quite hard to envision what's actually happened in the background, because if we remember, our system-based approach is a watts per liters per second comparison between our proposed design and our reference design, or DTS reference. So let's try to demystify what these percentages are. So just as a reminder, going back to our food analogy, we are comparing our proposed design, so you have changed breakfast, to your DTS reference breakfast or pumping system. And we're looking at the pump hydraulic power, watts per liters per second flow. So a few equations might be useful here. So the first is the equation for hydraulic power. So we know that your watts per liters per second is a function of your total system pressure divided by pump efficiency. We also know that with straight pipe work, we have our equation here that denotes what the losses of pressure drop, our pressure losses are. And then on our fittings side, we also know what the formula, which is a function of your fitting loss coefficient that can usually get off from the AIRAH technical handbooks. And it's also a function of fluid velocity. Now, in theory, if you were to do a calculation, you will be trying to assess it based on the hydraulic power equation. However, for simplicity, what the ABCD pump calculator does is it exploits the relationship between the pipework, straight pipework losses equation and the fittings pipework, fittings losses equation to simplify it based on a relative lift difference. So it's not actually doing the hydraulic power calculation, it's taking a reference. So we'll go through that example shortly. So what it's looking is to say is that says, okay, well, we know that with straight pipe work, the head loss is proportional to the square of the fluid velocity. And similarly, my fitting pressure loss is also proportional to my fluid velocity. Therefore, if I decrease my pressure loss by for my straight pipework component by say 10%, my fittings pressure loss reduction will also be 10% because of that proportionality assumption, and therefore overall my my system level watts or my hydraulic pump power based on the hydraulic power equation will also be 10% less. Okay, so that's the assumption that the ABCB pump calculator uses to simplify the process. Now we know that this is not always true, because when we look at our fittings equation, there is actually a KT function. So it's not strictly, it is proportional, but that percentage change is not always going to be the same. You know, you don't end up with 10% reduction in pipework losses equals to 10% reduction in fitting losses. And what I've done here is I've just plotted two examples here where you can see the KT, or the fitting loss coefficient for a copper screwed globe valve. You can see that as the nominal pipe diameter changes or increases, the KT, it's almost an exponential relationship, and something similar but not as evident for a T-branch, a steel T-branch. The ABCD pump calculator disregards this KT effect for an approximation. So what we can do is do a manual check of the results that we saw from the pump calculator just before. So again, we're looking at comparing the reference system versus the proposed system. So we know that the reference system, in the reference system, just by taking the values from the pump calculator spreadsheet, we can see that the reference should be 290.8 pascals per meters, but my proposed system is 157. My pump efficiencies that I should meet is 81.3%, but my proposed pump is only 78%. And now we need to do the calculations. So the relative difference is calculated for the straight pipework pressure loss. I've just taken 157 divided by 290.8%. So it tells me that my straight pipework pressure loss is 54% off my reference, or in the calculator you see it's 46% better than my reference system. Then for pump efficiency, what I've done is taken 81.3%, which is my reference, divided by 78%, and that tells me that my proposed pump efficiency is 104% of where I need to be. Or the calculator would tell you that you're 4% worse than your reference. And then what it then does is just to do a multiplication. So it's taken 54% multiplied by 104%. That tells us that my proposed system is 56.3% of reference, or in a calculator, you will see that it tells you it's 44% better than your reference system. So this is how you can do a manual check. And if you didn't want to use the pump calculator, you can probably replicate this calculation as well on your own. So in conclusion, we've gone through two ways to comply in the 2019 code. One is component-based and one is system-based approach. We've looked at the impact of changing operational hours, where we've said if you were running a system with longer hours, then you are allowed lower, so more stringent straight pipework pressure drops. If you were to use a constant speed pump, or your system was constant speed, then you're also subject to more stringent maximum allowable straight pipework pressure drop requirements. We also looked at the impact of changing your pump staging design. So we went from lead lag to duty standby, which equates to higher flows without changing pipework, which means that now my velocities through some stretches of pipework will be higher. And you can see that doing that leads to a higher BEP. So now we need 81.3% of some instead of something lower in a duty standby, lead lag configuration. And finally, just as a reminder, there's still pipework installation requirements that must be met, covered in Part J 5.8, that we haven't covered in this presentation. Okay, so that's it. This is relatively long.
Thank you for that, Grace. So just a reminder, everybody, if you do have any questions, please type them into the Q&A function, and we'll go through those ones now. So Grace, I can see a few questions have already started to come through. Do you have those ones open up on your screen?
Yep.
Perfect. Well, we can start going through those if you like.
Okay. So the first one is John's question. So how do you get to 5,000 hours per annum? Is it a accumulation of the number of pumps running? Yeah, it's basically how long the system operates for. So if you had, let's use my lead lag standby configuration. Obviously, the lag pump may operate less hours than my lead pump. But I'll be looking at the whole system and saying, actually, my whole system operates 8,760 hours per annum. So we're looking at a system perspective. Another one. So there's a few questions here relating to application of the Section J requirements. Whether it applies to cold storage warehouses using glycol as a refrigerant, or whether process cooling pumps need to comply with this. There is, if you look at the definition of air conditioning system, I actually have that written somewhere. It's actually looking at, it's typically looking at the, let me just see if I can bring that up. Yeah, so the definition in Section J says, for air conditioning for the purposes of Section J of Volume 1 means a service that actively cools or heats the air within a space, but it does not include one that directly cools or heats cold or hot rooms, or where it needs to maintain specialized conditions for equipment or processes, if that's the main purpose of the service. So I would make a suggestion that when you're talking about some of these process cooling pumps, it's more than likely not subject to these requirements, but you just need to interpret that on your own and cross-check with the building certifier. So there is a question about when a lead lag system is proposed, is the calculation based on both systems operating, so the total flow of both systems, or flow from a single pump? So when I'm looking at the pump efficiency component, I'm looking at the flow through that pump. So even though my total system flow in the first part of that work example was 67 liters per second, when I do my pump efficiency calculations, I'm using 37 liters per second. So we have a question here about whether a system is what is the difference between a distributive and non-distributive system? So for a distributive system, non-distributive, it's easier to go through what a non-distributive system is. A non-distributive system is a pipework system that doesn't have branches and it has the same flow throughout the whole system. So then that would fall under non-distributive. But for most HVAC applications, you'll be looking at distributive because you've got multiple branches. So water is being distributed to multiple legs. So the question is, please clarify on the interpretation of taking the average loss per length of the full piping index run. Note that the tables in Part J are per pipe diameter and fittings and valves are not applied in the assessment. Does this mean that the assessment is per diameter section, not the full pipe run loss average? So what all it does is you have, obviously when you're doing your pipework pressure drop calculations in a real design situation, you would have your fittings losses, and then you will have your straight pipework length. So all you'll be doing is you're taking only the straight pipework components, and you would have the pressure loss associated with that length of pipework, straight pipework. So you sum all of those. So let's say in a system, in a real system, in a full system, your total loss may be, 200 kPa, but your straight pipework component for sake of illustration here may only be 100 kPa. So you would be using your 100 kPa because that relates to your straight pipework pressure loss, and then you divide it by the total length of your straight pipework index run.
Thanks for that, Grace. So just another one that we've got there from David, who is asking, is this all applicable to a condenser water system for refrigeration process system, i.e. retail, supermarkets, etc.?
Okay, yeah. So the definition of air conditioning talks about a service that heats or cools the air within a space. I would suggest that you cross-check this with your building certifier again, but my inclination would be that a condenser water system for a refrigeration process system probably wouldn't be subject to these requirements. Because its main purpose is to maintain specialized conditions for a equipment or process.
Thanks, Grace. So just another one there from Matthew, who's asking, does Section J take into account the Pumps Australian standard, whereby they have a plus or negative 10% on the flow?
Yeah. So the example that I've used there already accounts for typical safety margins that will apply for, fouling in a system, for example. And it also already accounts for that, I guess, your plus and minus flows. Now, the code itself doesn't tell you exactly which point you would use, whether you use your KPA at, if your calculations tell you that it is 100 KPA, and for your safety margin, you have your pump, which is that plus, so 110 KPA. The code doesn't tell you which one you would use. So it'll be basically based off your selection and what the attributes for the individual elements are at that point. Okay, so the ABCB calculator, so there's a question about whether the ABCB calculator can be used to calculate a system pressure drop. No, it can't be used to calculate your system pressure drop. So you have to do that yourself.
So we've got Yossi, who's asking, we often use inline centrifugal pump from Danfoss TP series. I could not find the MEI from the data sheet. Have you encountered this?
I have, no, I have not encountered this. There's two options for you there. One is obviously to go back to Danfoss to ask for that information. And if they don't have that information, you can calculate it using your pump best efficiency points and your flow and head associated with that.
Special thank you to you, Grace, for conducting today's session. Just to let everybody know that this webinar has been recorded, and we will make this available up on the AIRAH website over the coming days. And I'll send out an email to all attendees today and let you know when that does become available as well. To view and or register for any of AIRAH's other upcoming webinars, please visit the AIRAH website. And if you're not already an AIRAH member, please consider joining, as not only we have the opportunity to expand your knowledge and skills, but also have access to many of our resources and tools as well. So thank you everybody for attending today's webinar. Thank you, Grace, and we look forward to seeing you at our next webinar shortly.